Hello, welcome to another problem session. You can see I have cold, and so my voice will not be very clear today, but I would like to continue recording one problem a day. Okay, so what do we have here? So this is a problem in spherical waves. It's So we've talked about waves which were like y, x, t, has some amplitude and some cosine kx minus omega t plus some phase constant, right? So these are examples of plane waves. These are plane waves. In 3-dimension, if you think of this as 3-dimension, maybe you want to call it psi, so don't confuse with y-axis. If this is x, and maybe this is y, and this is z, then this kind of wave, if you take any plane in parallel to yz plane, this wave moves in this direction. The value of this wave will be same everywhere. Over here is going to be another value over here. So each plane has the same value. So it kind of looks like a planes of constant value. Say for example, this was 1.2, this is minus 0.5. So every plane will be labeled with a value of the wave function. So this is plane wave, and the value is okay. So at a different time, this value will be different, because the wave moving, okay, but this value will be throughout the plane the same value. It's called plane waves, okay. When you look at thing which is multiplying this, the harmonic function, this part is harmonic function, and so this part is the amplitude. Now compare over here, this is the harmonic part, which is similar, but here r is not x, r is the radial distance from the point source. So over here we have a different picture. We have a picture, and this thing is kind of spreading out. This picture is spreading out, and so it's some distance r from a point source. So we're looking at over here. Now what's the amplitude? This amplitude is actually depends on the distance. So there's one amplitude for that distance. Maybe this is 0.3. And if I go another distance, so in that distance it's the same amplitude, and that it may be 0.1, but it will be same. And over here, if you look at this a value, it's so in here a is say 1.5. Over here a is also 1.5. So this thing is same for every plane. But over here the wave actually depends on how far away from you are, so in terms of the amplitude itself. Okay, another thing that I have included here is diameter of the sun, which is, you can look at 1.4 times 10 to the 9. This distance is very small compared to, say, the distances we're going to work with, okay. And in that sense I can take sun as a point particle, okay, a point source. Sun is pretty big, but in the context of these distances, it can be taken as a point source. So you might say the picture is the sun is like that, and all the distances are very big. This is even too big. I should be drawing a very tiny one, and that's why it's a point. Of course, you can see that over here, there's a problem here. This amplitude will blow up right at the center of the sun. So we want to say R not equal to 0. Okay. So that's one thing we should notice. And second thing is the formula for intensity. Formula for intensity, you know, this is going to be electromagnetic wave. So we're going to talk about how one gets this formula in much later, maybe almost 6-7 months from now, because when I will be in the optics. But right now we just have to take this formula, that formula of the intensity of EM, electromagnetic wave will be it's going to be like that, related to this. When the distance R is given to me, so like at this distance, for this distance, it will be same intensity at every point of this, but it will be different over here. The intensity will be different. Actually, this will decrease as you go further. If you apply that over here, the intensity here is same as intensity here. So here intensity doesn't decrease and is same in both of places. That's a plane wave. Plane wave, it keeps the intensity as it goes. Okay, this is an ideal thing. It's actually not very practical, but mathematically this is much easier to work with. That's why we work with this. All right, so the problem is at Earth, the intensity of sunlight is this. That's given to us in numerical value. And speed of light is c, and this is the epsilon naught is electric susceptibility of vacuum, electric susceptibility of vacuum. And you can look it up. This, I think this is 8.8 times 10 to the minus 12 in the SI units. It's kind of complicated units over here. Okay. All right, so I think that's set up, and so from this data we're supposed to find this part which is constant, doesn't depend on the distance. Find that part. In terms of units, you can see this will be units of voltage, because electric field unit is voltage, potential over distance. Okay, now find the intensity at Mars. So this is another interesting question. So what will be the intensity at Mars? Okay, so with this setup, maybe you want to see you can get this problem. Everything is here, and I think it's rather easy problem to do. Okay, let me clean it up and I can do it numerical answer. All right, okay, let's do it. So I have equation 1 and you have equation 2. So R0, so want to use this value to get V0. So let's write down I equals to half C epsilon naught V0 over R0 square. And so this, moving this over here, C times epsilon naught. So these guys go over there, and then they become square root. That goes out there. R0 goes out there. So that's the answer, with I given this and R given the Earth to Sun distance. So numerically, so let's work it out in a Python script. So here is a Python script for me. I imported math, and so let me put the things. R0 R0 is the distance, which is 1.5 times 10 to the power 11 in the meter. That's the distance from Earth Sun distance. And I've got intensity is equal to 1.36 times 10 to 3. Then I got the I, and then the C equals 3 star 10 8. Epsilon 0 is, I think we're going by my memory, minus 12. Okay, I think we have all the things. So R0 I C. Okay, so the V0 is supposed to be R0 times, take a square root of the stuff that we got, 2 times I divided by C star epsilon 0. I think I have all of them right, so then I can print that, and I see I got huge value here is 1 2 3 4 12 12 and 14. So I got this answer 1.5 times 10 to the 14, and because this is volt, SI unit is volt, so it's gonna be that many volts. Okay, so that's A. All right, how about B? Now I've got this, we need to get the intensity. We can use the same formula but with R0 now mass. So we just, I is equal to half C epsilon naught V0, that we're gonna plug this in here, and divide by this 2.24 times 10 to the power 11 square. But this is actually not necessary. You can see that all this extra thing you have to put, look at this part. This part is common to this intensity if this was the R of the Earth Sun distance. So we do half C epsilon naught V0 square over the 1.50 times 10 to the power 11. That's the Earth Sun. This will be the intensity at Earth. Intensity at Earth, right? So I divide by this, then I multiply by this over 2.24 times 10 to the power 11 square. So this is much easier to do. I'd rather have all this extra stuff go there. So this is just this value. So that just becomes, for me, 1.36 times 10 to the power 3. And you can see all this, I have the same units and they're of the same scale, so it's pretty easy in terms of scaling. 1.50 over 2.24 square. So I can just work out this number pretty easily. So So I have I star 1.50 over 2.24 square it, and so the intensity will be actually is much smaller. So it will be equal to 610 watt over meter square. Well, this was 1360 watt over meter square. Okay, so let me we've already got the answer. Okay, let me tell you something quite theoretical here and interesting. So an erase, and so let's look at a theoretical. This is a theoretical extension. So if I look at this formula I from this, so the intensity at a distance r, instead of r0 there, at any r is actually equal to half c epsilon naught v0 square over r square. So these are not changing with distance, so this comes some alpha over r square. And so this intensity actually you know, if the distance, if r becomes, start from r0 and you have r1 equals to r2 equals to 2r0, if this intensity is I1, then I2 will be 1/4 of I1. If R3 is 3R0, 3 times the what I1 was, so this makes I3 equals to 1/9 I1. So you can see the intensity is actually intensity at a distance r is actually going 1 over r square. And this quadratic dependence means intensity will drop off very rapidly, and this has to do with, you can see that also that this must be related with the energy conservation. All right, so let's look at, here is some distance r1. So this is a spherical surface which is 4 pi r square in area. So say r1, this is r1, and intensity, if you remember, intensity is energy per unit time per unit area. So if you multiply by the total area, it will give me how much energy is flowing through all of it per unit time. So all the energy that's flowing over there has to go somewhere, right? The light has to pass this surface. So same amount of energy has to pass through this surface. So it tells you that this distance is 4 pi r2 square. And so if the intensity here is I2, intensity here is I1, then the energy crossing that energy per unit time, energy per unit time is the same from both of them, and one is I1 4 pi r1 square, and other words I2 4 pi r2 square. This tells you that I2 over I1 will be related to quadratic. I2 will be r1 square over r2 square. This is a very important result, and this problem kind of illustrates an application of this result. So I hope you you understood this. We'll probably use this without even mentioning this in some time, that if you have a point source of light from if you have, it's very important to not just blindly use this formula. Don't use blindly, okay? Because it's only possible because of what we just assumed, right? We had a point source of light at the origin. We had a point source of light at the origin, and so we model it as a spherical wave. When you have a spherical wave, then the intensity will go this way. So you got to remember the whole situation here, all right, before you use this formula, which is quite useful actually. It tells you how if I have a sun here and you have at various planets at various distances, the intensity will drop as a square root of the distance. And also tells you why if we are here, this is the Earth, and very far away planet, a very far away star, which maybe is as bright as the sun as we started out, but when it gets here, this distance is so much more that it's going to become very dim. So dimness of stars of same absolute brightness as sun can be understood quantitatively using this logic. Okay, I'm going to stop here. I'll talk to you later in the video. Bye.